Okay, so you've seen some examples of single particle and two particle states, and we've calculated the overlaps. You should easily be able to write down now an n particle state for any n and calculate the overlap between those states. So, for example, you should very easily be able to see that this overlap is equal to 0. So please play around with this a little bit. Write down some states of your own and calculate some inner products. Now I want to move on, and I want to give you an example of an operator inside Fock space. So for example, the Hamiltonian would be a sum over P, omega P, and then we would have a dagger P, A, P. So this is a good example of an operator in Fock space. And I want to show you how do we use this operator to act, for example, on a single particle state. So let's apply H to the state K. So let's first of all write down the Hamiltonian. So this is just going to be a sum over P, omega P, A dagger P, A P. And then our state K is A dagger K acting on K naught. Okay? And by now, the logic should be clear. What do? I always add terms to what I've got with the condition that the terms that I've added are 0, so it doesn't change the expression. But after adding the terms, what I've got can be identified as a commutator. And the reason why I do that is because the only data that I know about these operators, the thing that defines these operators, is these two red boxes. So it's always the commutator that I'm using, okay? So take a look at what I've done here. I've added an extra term. This extra term is 0 because AP will annihilate the vacuum. But the good news is the terms inside that round bracket are now easy to evaluate using the commutator. So this will be a sum over P, omega P, A dagger P, and then the value of this round bracket using the commutator is delta PK onto naught. And now I can sum over P. Every single term in the sum is 0, except for the term with P is equal to K. And in that case, the delta function just gives me a 1. So I'll get omega K, A dagger K on K naught. And this is omega K onto the state K. So indeed, we see that the single particle state is indeed an eigenstate of the Hamiltonian with the correct energy. Let's just do one more example. Let's take the Hamiltonian and let's evaluate it onto the two particle state. Okay. So again, this is going to be a sum over P, omega P, A dagger P, AP, and then I've got A dagger K1, A dagger K2 onto the vacuum. And what do? Well, now you should know I'm going to start off by adding a term. So I've got A dagger P, I've got AP, A dagger K1, A dagger K2. Then I will subtract A dagger K1, A dagger K2, AP, and then the vacuum. And the second term that I have added is 0 because AP annihilates the vacuum. But the nice thing is now, well, again, no shock. This is a commutator. And it's the commutator between AP and A dagger K1, A dagger K2. How do I evaluate this commutator? Well, by using the product rule. So let's do that. So first, the commutator acts on A dagger K1, and we leave A dagger K2 alone. And then the commutator will act on A dagger K2. And now let me plug in the value of the commutator. That commutator is a delta P1, K1. We've got an A dagger K2 plus, and we'll have an A dagger of K1, and that commutator is AP K2 naught. And again, these delta functions allow us to do the sums. So for the first term here, we only get a contribution when P is equal to K1. So we get omega K1, A dagger K1, then we've still got the A dagger K2 and K vacuum plus. And for the second term, we only get a contribution when P is equal to K2. So we get omega K2, A dagger K2, A dagger K1, and then K vacuum. But you can see these two states are the same. So I can pull out omega K1 plus omega K2 onto A dagger K1, A dagger K2, and Ket naught. And this is omega K1 plus omega K2 onto the two particle state K1, K2. So we see that the two particle state is indeed an eigenstate of our Hamiltonian with the correct energy, the energy that we expected, just the sum of the energies for the particles. You should go ahead and check that you would be able to calculate the application of the Hamiltonian to the three particle state. Let me give you another example of an operator that you could study. So the momentum operator P would be a sum over P. Then it would be P, the momentum, a dagger P, A, P. Why don't you apply this momentum operator to the single particle state, the two particle state, and check, does this give you the momentum of the state? Okay, so here are two very natural operators to write down in Fock space. Okay, good. Now, I would like to just make a comment contrasting what we've done with Fock space to what we did with the oscillator. So remember what we did with the oscillator? We said we had a spring with a particle attached at the end. Okay, so there's our oscillator. And then, so let me just copy this picture. Okay, so there it is. Good. Let me copy it. Duplicate. Good. So there it is. And let's copy it again. Duplicate. And there it is. Good. And what we said was, we said that in general, this oscillator will oscillate with some size of oscillations. And you can't oscillate with just any oscillations. There's a discrete set of oscillations that you can have. And by using the creation operator, we add one packet of energy to the system. So there's always just one particle that's oscillating. But when we act with a dagger, we increase the oscillation of that particle. When we act with A, we reduce the oscillation of that particle. Oh, let me remove that dagger. So there was always just a single particle, but we were adding energy to the single particle, adding a packet of energy or reducing a packet of energy. We now have a rather different picture. So what do we have? Well, we have a box. So there's our box. And let's duplicate the box. No, let's duplicate the box. So there we are. Duplicate. There we are. Let's duplicate again. And there we are. And we might start off with a box that has got nothing in it. Okay. And then a moment later, we've got a particle with momentum K1. And we might want to create a second particle with a momentum K2. Let me do this a bit better. Momentum K2. Now, what is happening in our system is that to go from the box with no particles to the box with one particle, we act with a K1 dagger. To get the box now with a second particle, we would act with a K2 dagger. So now we're using the harmonic oscillator in a very different way. In the old way of thinking about the harmonic oscillator, a dagger added a packet of energy to our system, and it changed the size of oscillations of each particle. Now, when a dagger acts on our system, it adds a particle to the box. So this is a very different use of the harmonic oscillator. Pay attention to that, and maybe it requires you thinking a little bit about it. Okay, good. That completes our discussion almost of Fock space.